Now in this video lecture we will go through non-stoichiometric defects, right? Before this video lecture we have done Scotty defect and Frankel defect, right? Those defects were stoichiometric defects, right? By saying stoichiometric defects, we mean that due to those defects, Frankel and Scotty defect, the stoichiometry of the compound is not disturbed. That is why they are stoichiometric defects, right? Now, when we talk about non-stoichiometric defects, in non-stoichiometric defects, the stoichiometry of the compound would not be maintained. That is, the stoichiometry of the compound would be disturbed, right? In non-stoichiometric defects, here stoichiometry would not be maintained, right? And if you remember, there were two things, right, when we were talking about defects in crystals. The first was stoichiometry, which we said in these types of defects it would not be maintained, right? We'll see how in a moment. Then the second thing is electrical neutrality, right? Electrical neutrality would be maintained as in stoichiometric defects, right? So electrical neutrality would be maintained, right? Now we'll just consider these 2 points when we study about regarding these non-stoichiometric defects, right? Now non-stoichiometric defects are of two types. The first is metal excess defect, right? And the second type of defect is where metal deficiency defects, we call it, right? Metal excess defects and metal deficiency defects, right? So these non-stoichiometric defects would be of two types, right? First is your metal excess defects. When we talk about metal excess, we mean the cations, which are metal ions, right? So metal excess defects, we'll see how crystals show metal excess defects. The other is metal deficiency defects, where the positive ions, the metal cations, will become less as compared to negative ions, right? So we may also call it as non-metal excess defects, right? We may also call it as non-metal excess, because we know that in a neutral compound cations is equal to anions, right? So if cations and anions are equal, when we say metal deficiency, that means metal cations, right, are deficient by certain numbers. That means when metal cations are deficient, that means anions are more, right, or anions are in excess. So let's talk about the first type of defect, right, which is your metal excess defects. Let's see how metal ions, that is positive ions, this A plus is your cation in this lattice structure, and B is your anion. Now we'll see how these positive ions, cations, become excess, right, due to what it become excess, right? So in these type of defects, metal excess defects, we have anionic deficiencies. Anionic vacancies, right? Anionic vacancies. When we say anionic vacancies, that means the sites that are occupied by anions will become vacant, right, in such defects, right? So if this is your anion, B minus represents your anion, right? So in these types of metal excess defects, which are anionic, right, anionic vacancies, right, How do these occurs? These occurs first by anionic vacancies. So the sites that are occupied by anions in this lattice would be unoccupied, right? And it will that will give rise to this metal excess defects, right? So by anionic vacancy we mean anionic vacancies is sites occupied by anions would be vacant, right? So these, say this anion, right, B minus is an anion, say B minus anion is missing from this lattice site, right? So it will give rise to this metal excess defect, right? Now let's see what happens when this anion, right, when this anion would be missing from its lattice site. It's a negative ion, it has a negative charge, right? And we said here that electrical neutrality would be maintained, right? If B minus, right, is missing, this anion is missing, then to maintain electrical neutrality, this site would be occupied by a negative charge, by a particle that has negative charge, so that it can maintain the electrical neutrality of this compound, which is represented by AB here. A is positive and B is negative, right? So if B minus is missing, right, from its lattice site, then the place of this anion would be taken by an electron, right, which is a negative site, which is a negative particle, right? So this site would be occupied by an electron, right? So this is when we said here the sites occupied by anions would be missing and would be occupied by an electron, E minus, right? And this site, right, now we said this B is missing, right, and the place of this B would be occupied by electron, right, to maintain the electrical neutrality, right, to maintain electrical neutrality. Right. Now, due to this electron which has occupied an anionic site, right, this crystal of sodium chloride, this crystal of this compound AB, right, would appear colored, right? Now let's say if this is a sodium chloride crystal lattice, right? Now if this kind of defect is found in sodium chloride, then sodium chloride compound would appear yellow due to this electron that has occupied this anionic site, right? So these sites, right, this site which is occupied by electron, these are called as F centers, and these are also called as colored sites, right, or colored centers. I'm sorry, we call it as colored centers. Or if in your books we call it as, you will find it as written as F centers, right? F is nothing, we call it F centers because F means Fabre, which is a German word for color, right? So these are colored centers, right? F is your Farbe. Which in German means color, right? So these F centers are colored centers. Due to these F centers that are occupied by electrons, this crystal would appear colored, right? Now let's quickly see how this anionic site would become vacant and how the place of this anionic site would be occupied by this electron, right? This happens, let's say sodium chloride will appear yellow when heated in atmosphere of sodium vapors, right? Now suppose you have some sodium chloride here, right? And you are heating it in the atmosphere of sodium vapors, right? This is your sodium chloride, and the crystal structure or the crystal lattice of sodium chloride would appear like this, whereas A plus represents Na plus sodium ion and B minus represents Cl minus anion, right? So now what happens is, when you heat sodium chloride in the vapors of sodium, right, this sodium chloride will appear yellow, right, due to this metal excess defect. Now let's see how metal excess defect will arise in sodium chloride when it is heated in sodium vapors. When you heat sodium chloride, right, what happens is, when you heat sodium chloride, this one chloride ion, right, which is an anion, right, will be removed from its site, right, will move, right, or get removed from its site, and will go at the surface, right, where it will combine with sodium ion to form sodium chloride, right, and this chloride ion will react with sodium, when sodium will lose an electron, right, to form sodium ion, right. So this will lose an electron. Since we are heating sodium chloride in the atmosphere of sodium, it will form sodium ion, right, and this chloride ion, right, which is present at one of the sites, right, it will move from its latticed site, right, and will go to this sodium ion, right, and will react with it. The sodium ion and chloride ion will react to form sodium chloride, right, and this electron which is lost, right, will move into the crystal lattice of sodium chloride and will occupy this anionic site, the sodium chloride, which is removed from its latticed site, right. Now this site, the anionic site, would be vacant. This site, the chloride site, would be occupied by this electron which is lost by sodium ion, right. So this anion will move, right, inside this sodium chloride lattice and will occupy this vacant site of chloride ion, right. So it will form an F center. This electron will form an F center by occupying the chloride anion site, right. So what we say is that this electron, right, which is this electron is, we call it like this electron is trapped in anion vacancies, right. We say that this electron is trapped in anion vacancies and is responsible for giving yellow color to sodium chloride, right. So this is how this kind of defect is generated when sodium chloride is heated in the vapor of sodium, right. So I'll repeat quickly. When sodium chloride is heated in the vapors of sodium, the sodium chloride will appear yellow, right. Why? Due to these F centers that will get developed in the crystal lattice of sodium chloride. Now how this F center will get developed? When this sodium chloride is heated, one of the chloride ion will leave its place, right, and will move and will react with this sodium, right. This sodium will lose an electron to form sodium ion and will react with this chloride ion which is missing from its anionic site to form sodium chloride, and the electron which is lost by this sodium metal atom will move in the crystal lattice of sodium chloride to occupy the site, the anionic site from where this chloride ion is missing, right. So this is known as a colored center or F center. Why we call it a F center? Because of this German word Farbe, which means color. right? So these F centers are colored centers that are responsible for giving color to these crystalline solids, right? Similarly, if so what we say is this crystalline solid is colored due to excess of sodium ions, right? And what actually happens is, we know that in the crystal structure of sodium chloride, one sodium ion, right, one sodium ion is surrounded by six chloride ion, right? This is surrounded by 6 chloride ions. Similarly, one chloride ion would also be surrounded by 6 sodium ions, right? Surrounded by 6 sodium ions. So when let's look at this F center. Now this electron, right, would also be shared this six chloride ion, this sodium ions represents the coordination number of chloride ion, because these 6 sodium ions are immediate neighbors of this chloride ion. So when this chloride ion is replaced by this electron would also be shared by these sodium ions, right? So this electron is similar to, this electron is not localized to any one of the sodium ion, and this electron we call it as delocalized. We call it as delocalized electron, right? Because it is shared by all these sodium ions. And this is now similar to the conjugated system that we see in conjugated organic compounds, right? And how it gives color to these crystalline solids, these electrons will occupy light energy, right, and will move to higher levels, due to which these crystals will appear colored, right? So this is important, these F centers, and how do they appear colored. The electrons will, what they do is basically they absorb energy of white light, giving yellow color to sodium chloride, right? So this is important, these electrons will absorb light, right, and when they absorb light, they will do transition to higher energy levels, right, and will absorb light and give yellow color to NaCl, right? So similarly, if you take example of sodium, if you take example of potassium chloride, so potassium, when you heat potassium chloride in excess of, when you heat potassium chloride, right, when you heat potassium chloride in potassium vapors, right, this crystalline structure or the lattice of potassium chloride will become excess in potassium ions, right? So excess of potassium ions will give it pink color. Like here in sodium chloride we see yellow color, here we get pink color, right? Because one of the site, again the missing anionic site due to this chloride ion, the vacant anionic site due to chloride ion would again be occupied by an electron, which will make it appear pink, right? When they absorb light, they will make this potassium chloride to appear pink, right? Similarly, we have another example where lithium in lithium chloride, right, makes it pink. In this case, in case of potassium chloride, potassium chloride will not appear pink, it will appear violet. It's lithium, right? It's lithium chloride. Lithium chloride will appear pink when heated in lithium vapors, right? So potassium chloride due to excess of potassium ions, right? Why excess of potassium ions? Because one of the chloride ion would be missing from its anionic site and would be occupied by an electron, right? So excess of potassium ions will make it appear pink. Why pink? Because electron that has occupied the anionic site will absorb light and will make it to appear pink. Similarly, will make it to appear violet. Let me write it over here. Sorry for the confusion. It's violet, right? Similarly, lithium chloride will appear pink, right, when heated in the vapors of lithium, because one of the chloride ion would be occupy one of the chloride ion site, right, would be taken over or occupied by an electron, right? So now we have excess of lithium ions, due to which it will appear pink, right? And the electron, and how it appears pink, the electron that has occupied the anionic site, which we call it as F center, will absorb light and will make it to appear pink, right? So this is your metal excess defect that comes under anionic vacancies, right? Now the second type of this defect is kind of a vacancy defect, right? Because a vacancy that has generated due to the anion missing from its site, right? We have this defect, right? Because when the anion is missing, the place is taken over by the electron to maintain the electrical neutrality of this lattice, right? So this is a Schottky defect. This is similar to Schottky defect, right? And this kind of defect is found in those crystalline solids that showed Schottky defect, right? So just remember that since this is due to vacancy defect, anionic vacancy, this is an anionic vacancy defect, right, which is a vacancy defect, so is same as Schottky defect, and this kind of defect would be shown by those crystalline solids that show Schottky defect, right? Now what about the stoichiometry? Stoichiometry, you can see that stoichiometry is not maintained. Why? Because we said we have excess of metal ions. One of the anion is missing from its site. So now we have one anion less, right? And if we talk about sodium chloride, right, we said it appears yellow because now we have one chloride ion less than the original sodium chloride, right? Because that one, and the site of that one chloride ion would be taken over by an electron. So the stoichiometry, that is 1:1 ratio, would not be maintained in sodium chloride due to this metal excess defect, right? So if after this defect we may write the formula of sodium like 1 minus delta, right? Because we have some chloride ions missing, maybe more than one, depending on that depends the value of delta, how many chloride ions are missing due to these defect. So it would be like this. So here electrical neutrality is maintained because that site is replaced by another negative particle, which is electron, but stoichiometry is not maintained because that chloride ion is moved from its lattice site, right? And these kind of defects also does not follow law of constant proportions. Law of constant proportion says that if I take sample of sodium chloride from any source, right, the ratio of sodium to chloride ion would always be 1:1 as per law of constant proportions. But here we see that this sample of sodium chloride, in this sample of sodium chloride, ratio of sodium to chloride ion is not 1:1. So this does not, due to this defect, sodium chloride does not follow the law of constant proportions, right? I hope this is clear to you. Now we move on to the other kind of defect, which is your metal deficiency defect, right? Not metal deficiency, we have another type of defect. We have another type of defect here only. This is your Schottky defect, which has Schottky-like defect, which has generated due to anionic vacancy, right? We have another type of defect, which is due to a cation that has occupied an interstitial site. Now here the B is there, right? Now a cation will occupy in another kind of defect, and the cation will occupy a interstitial site, right? If this is a similar kind of lattice, suppose an cation that has occupied the interstitial site, let's say this is the cation A plus that has occupied the interstitial site, right? Now we have an excess of A plus ion, right? So it will make this crystal lattice more positive, right? So to maintain the electrical neutrality, we need one more negative ion, right? So we have in another site, you will see an electron that has occupied the neighboring interstitial site, right? Now since interstitial site is occupied, this is similar to Frankel defect, right? This is another kind of second type of defect, and due to this defect you have a cation in one of the interstitial site, right? And since you have cation in one of the interstitial site, so to maintain the electrical neutrality you need one negative ion. So in the neighboring or in another interstitial site would be occupied by an electron, right? Cation in one of the interstitial site and electron in another interstitial site, right? To maintain electrical neutrality, right? Here stoichiometry is not maintained because here we have extra cation, right? So here the formula would be, if this is a compound AB, then A would be 1 plus lambda B. We have excess of metal cation, right? So this is a metal excess defect. And how we get this? If you have a zinc oxide, this kind of defect is seen in zinc oxide. When zinc oxide is heated, right, it will form zinc ion plus half oxygen, plus we know zinc is divalent, so it will lose 2 electrons and will form zinc ions, right? So this zinc ion, if you draw the similar crystal lattice of zinc oxide, this zinc ions would be present in this interstitial sites, right? And this electron would be present in the neighboring or in other interstitial sites, right? So this is how this interstitial defect takes place, right? And since this is interstitial defect, the interstitial sites are occupied. This is similar to Frankel defect, because you remember in Frankel defect also the interstitial site was occupied, right? So here also the interstitial sites are occupied, right? This is occupied by metal cation. We have seen that we have taken this example. When this is heated, it will form cation, which will move to interstitial site, and these electrons generated would move to another interstitial site to maintain the electrical neutrality, right? So here we have more zinc ions in the crystal lattice of zinc oxide. So this is metal excess defect now, right? I hope this is clear. And so due to this defect, this will appear yellow. Zinc oxide will appear yellow, right? So this is your metal excess defect. There is another metal deficiency defect. In metal deficiency defects, what happens is, there is metal deficiency defects. Here we have extra metal cation, so it has resulted into metal deficiency defect. If in the similar crystal lattice, actually these metal deficiency defects, right, these are shown by compounds that have variable valency, like iron, right? Iron has valency ferrous and ferric, right? So these kind of compounds will show metal deficiency defects, right? In metal deficiency defects, what happens is, in metal deficiency defect, the defect occurs when the metal shows variable valency, that is in transition metals, right? So the defect usually occurs due to missing of a cation, right, from its lattice site, and the presence of cation having higher charge in the adjacent site, right? We will do this defect in another video lecture, but quickly to understand, if say this is A plus, right? If this is missing,